Hello, this is Greg Risterman from Olympus. I'd like to welcome everyone today to this webinar titled Advantages of Ultrasonic Thickness Gauges over Flaw Detectors for Corrosion Thickness Measurements. This webinar highlights the advantages of modern ultrasonic thickness gauges for making corrosion thickness measurements. The presentation will focus on certain features that make thickness gauges better suited than ultrasonic flaw detectors for this type of application. Our presenter today is Greg Bauer. Greg is a product specialist for Olympus ultrasonic thickness gauges and transducers. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Greg Bauer. Greg, take it away.
Thank you, Greg. Thank you, everyone, for joining me in this webinar. Good morning, good afternoon, wherever you're joining us from. Today we're going to discuss, as Greg mentioned, the advantages of thickness gauges over flaw detectors for corrosion thickness measurements. I'm going to take us through this webinar. I'll be kind of going back and forth between the presentation and also be doing some live demos in there as well, where I basically share my screen so you can see the instrument screen and making adjustments and making measurements, things like that. So without further ado, let's get started. So first and foremost, this is not going to be an attack on flaw detectors. Flaw detectors are great instruments for a number of reasons. And to be honest, they're pretty similar to thickness gauges in that they use the same kind of basic ultrasonic concepts. They're both using transducers that generate sound waves. They both measure the time it takes for that sound to leave a transducer, travel through a material, bounce off of a reflector, and return to the transducer. So the basic equation that we use is distance equals velocity times time. We modify this slightly by dividing that time value by 2, since we only need the one-way time to the reflector. So with thickness gauging, it's typically straight beam types of inspection, and we're measuring the time of flight to the back surface of the material. So this corresponds to the total thickness of the material. Whereas a flaw detector, a lot of times, they're going to be measuring to like a defect or a void, so they can locate the distance to the flaw from the surface of the material. But one of the main advantages of flaw detectors is they're just plain more versatile. They can cover more applications. So not only can they measure thickness, but they can also use angle beam inspection to check the integrity of welds. They can also work for scanning applications, and they're actually a lot kind of better for scanning just because they have a faster update rate. So flaw detectors typically have about a 60 hertz update rate compared to most thickness gauges, which have about a 25 to 30 hertz update rate. So you can scan a lot faster with a flaw detector than you can with a thickness gauge. Also, because flaw detectors are designed for sizing defects, they're going to include specialized software for doing this. So we have distance amplitude correction, or DAC, time varied gain, or TVG, distance gain size, DGS. So with a flaw detector, the amplitude of the signal is absolutely critical, right? Because this is what's going to be used to basically size the defect. Based on the returning signal amplitude, you're going to have to determine whether or not that flaw is acceptable, or if it's large enough that it's a reject and it's a critical flaw. With thickness gauging, we're a little less focused on the amplitude of the signal, and what we're most focused on is actually the time of flight measurement. So we want to make the most accurate, consistent, and repeatable time of flight measurements as possible. So what it's really going to come down to is using the right tool for the job. What's the main goal of the measurement? If you need to detect and size voids, but you also want to measure thickness, then you're going to want to get a flaw detector. But if you want the most consistent and accurate thickness measurements possible, then you're going to want to get a thickness gauge. So way back, users didn't really like using thickness gauges, even just for measuring thickness. They actually preferred to use flaw detectors. So the early kind of ultrasonic instruments were developed and released in the late 1940s. The majority of these were primarily focused for flaw detection. The first digital thickness gauges, or D meters, as they eventually became known as, were released in the 1960s. But the big issue with these, and this is an example of one here, it's nice, small, portable, but it's just a digital readout. There's no actual waveform or A-scan to see what that digital reading corresponds to. So users didn't really feel confident using the thickness gauge because there was no way to verify what that actual reading meant. So if you're measuring along, it's supposed to be a 1/4 inch, everything's right in that range, then everything's good, but what if you all of a sudden get some drastically different number? So in the 1980s, right here, we released a thickness gauge with onboard waveform, and users really started using the thickness gauges. And today, these small, powerful instruments now either come standard with waveform or they're offered as a software option. So here we have 2 screenshots, and it shows why having a waveform or A-scan is so critical. So on the left, you can see we're detecting noise, right? But if you're only getting a digital readout and you only see this 0.075 inch reading, it's hard to know, is that a valid reading or not? But here you can clearly see that it's a detection of noise. And not only that, you can actually go in, based on the waveform, make adjustments to correct that issue. So in this example, you can either extend out the extended blank adjustment, or you could also lower the gain so that that noise signal is below the 20% detection threshold. So here's another example where the waveform actually tells you more about what you're measuring besides just the reading. So in both cases, we're getting the measurement to the back wall, but by having the waveform, you can see in waveform 1, the back surface is a lot cleaner because the sound's actually reverberating within the metal and generating these multiple back walls. In waveform 2, because the back surface is so corroded, we're only able to get one back wall signal. There's no multiples. So having waveform is key, which is why a lot of instruments now come standard with that. So this is going to be kind of the basis of the webinar, the advantages of the thickness gauges over flaw detectors. Specifically, we're going to be focusing on corrosion measurements. Some of these have started to narrow as flaw detectors sometimes now offer thickness gauge kind of modules and things like that. But for the large majority of instruments on the market, these still hold true. So right off the bat, size and cost. Thickness gauges are typically smaller and cost less than flaw detectors. One of the biggest ones is the ease of calibration and operation. And this is all based on the users of the instruments. So a flaw detector user is much more trained. They have to go through level 1, level 2, level 3. And because of that, the measurement is much more reliant on the user. So they have to set gates, they have to be able to read the waveform. With thickness gauges, the users are typically less trained. So what we do is we actually build into the software capabilities to take some of that reliancy off of the user and make more of kind of an automated measurement. So we'll discuss the various ways we do that, as well as the various ways that we make consistent, accurate time-of-flight measurements. And thickness gauges also have their own kind of specialized software for unique applications. So this includes boiler tube measurements, high temperature applications, and painted or coated applications. So the first advantages I want to focus on is the measurement advantages. So in this section, we're going to cover auto zero compensation, V-path correction, auto probe recognition, and also detection algorithms and digital signal processing. So with a dual element transducer, you have two separate elements, one that transmits and one that receives. It's kind of a pitch catch measurement mode. And as you can see, the actual crystal that generates the sound is bonded to a delay line. So what that means is the sound is not generated where it actually enters the material, which would be down here. So we have to compensate for that time through the delays. So what the auto zero feature does is it's used to calibrate for the sound through each of the transducer delay lines. And what's nice is as soon as a user plugs in a thickness gauge dual, they're notified of this process and actually get help text on screen, which kind of guides them through the process. So again, it's a very automated, very easy to follow process, and it's required before they can start taking measurements. So basically, they'll get a message where it says, please wipe couplant off probe, press second F, cal 0, and what that does is it measures the time through those delays. So this is particularly important because dual element transducers are used for corrosion applications. The transducer is going to wear over time. So this distance is going to change as the transducer wears. So the auto zero feature allows us to compensate for that change. Likewise, in high temperature applications, auto zero is really kind of crucial because as you're measuring that high temp application, these delay lines are going to heat up. So sound velocity changes with temperature, so that auto zero allows us to compensate for that change as well. So the total zero, so when you do a calibration, you do a cal velocity, which sets the sound velocity of the material, focusing on the sound through the actual material, and then you do your cal 0, which is the time through anything besides the material, so like your cable, your couplant, etc. So what's nice is every time you do an auto zero, it actually updates that total zero offset, so the time through the delays as well as the time through the couplant, cable, etc. And what this does is it allows for a more precise zero offset measurement, which then in turn obviously contributes to a more accurate time of flight measurement. So why are dual element transducers used for corrosion applications? You can see on the left you have a single element, one element that transmits and receives, kind of a pulse echo. The majority of the sound is being scattered by that rough back surface. You get very little sound being returned to the transducer. Whereas on the right, you have the dual, one element transmits, one receives. They're angled in towards each other, which we call the roof angle. And it causes those transmit and receive beams to cross under the examination surface. So whatever part you're measuring creates kind of a pseudo-focused effect. And this really helps increase sensitivity when you're examining a part that has a rough or pitted back wall. So dual element transducers for a very long time have been the industry standard for measuring remaining wall thickness in corrosion applications. But, there's a but. Because we're sending the sound at an angle, that's not the true thickness. True thickness would be straight in and straight out. So what our corrosion thickness gauges do is use something that we call V-path correction to compensate for that angular sound path. So this V-path correction allows for the highest degree of accuracy and repeatability over a large thickness range. So here's an example where we calibrated on a thick step right here, 1.5 inches or 38.1 millimeters. We did our cal-vel. We did our cal 0 on 50 thousandths or 1.275 millimeters. And what you can see is in between, these are the actual thicknesses that they should be. The actual thickness reading is off quite a bit, quite significant, because flaw detectors, most flaw detectors don't compensate for that angular sound path. So what's also nice is thickness gauge duals, the D79X series of transducers, include this center pin, which is an auto recognition pin. It allows the gauge to automatically recognize which transducer is being plugged in. So again, this makes it very easy for the user. It automatically recalls the optimized setup and receiver gain for that transducer. It also automatically recalls the predetermined V-path correction for that transducer. So it makes it very, very easy for the user to start taking accurate thickness measurements. They simply plug in the transducer. They're going to follow the help text on screen to do that auto zero. And after they've done that, the instrument has now recalled the V-path correction for the transducer and compensated for the time of flight through the delay materials. So now the user can calibrate on their material and start taking measurements. So if you're using a non-potted transducer where the cable and transducer are separate, you definitely want to make sure that you get the correct corresponding cable so that it has the correct center pin. If you're using a flush case dual or maybe a non-Olympus dual element transducer that doesn't have a center pin, the Olympus 38DL Plus actually allows you to create and save a custom V-path, which is really, really nice, having that ability with the 38. So these are basically kind of the steps of doing a V-path build. You do need a multi-step test block, and it should represent the same thickness range and material that you're going to be measuring. So you want to make sure you have your minimum and your maximum thickness in there. So the V-path comes standard on the 38, the V-path builder, but you do have to enable it in the setup menu. And once you do that, you'll actually be prompted to build a V-path when you press the CalVal key, and you have the option to choose yes or no. You are required to measure on at least 3 steps of the test block, but you can do up to 10. Using more calibration points is going to improve the V-path correction. And then once the V-path is complete, once you've entered in all those steps, you have the option to save that custom dual element transducer setup, which will actually include the V-path data. So then it makes it very easy to use this transducer in the future because you don't always have to be building a V-path. You can just recall that setup for that transducer. So one thing I do have to say is that Olympus cannot guarantee the accuracy or performance with non-D79X thickness gauge dual element transducers. You just want to make sure that if you are using a non-Olympus dual, it's making the proper and suitable detection for your application. So what I want to do now is actually show what that V-path builder looks like and the advantage of having it. So I'm going to share my screen. So I'm using a USB to VGA adapter so you can actually see the screen of my instrument. So I'm using a transducer where the cable doesn't have that center pin. It only has 2 LEMO connectors. And when I plug it in, the 38 automatically recognizes that I don't know what this transducer is. So right off the bat, the first step is to try one of these generic setups. This is going to have some type of V-path built in, so it may or may not work. So I'm using a 2¼ meg transducer, so I'm going to choose that 2 megahertz setup. So then I press the red measure key. So this is that auto zero feature, so it's nice to get this help text. So please wipe coupling off probe, then press second F, cal 0. Second F, cal 0. Gauge measures the time through each of those delay lines. So I'm going to be measuring on a 4-step test block from 1.5 inches, then the next step is 0.75 inches, then 0.3 inches, and then 0.15 inches. Change my range so we can see the signal on screen. So as soon as I press CalVal, I get this user text. Measure thick standard, then press enter to continue. Press enter. Then again, enter thick standard value, then cal 0 to measure a thin standard. So I'm going to adjust this down to the known thick, and then press cal 0. Follow the same process for the Cal 0. So if you're ever unsure of how to calibrate using a thickness gauge, we give you this nice user guide text. So after I enter in the thin, I can press the red measure. So now you'll see on the 150, it reads correctly. When I go to the 300, I'm about 9 thousandths off. And 750, same thing, about 10 thousandths off. And 1.5, I'm reading correctly. So what I want to do now, because those steps in between really weren't within the accuracy that I want, or the specification for these transducers. So what I'm going to do is turn on that VPath builder. So if I press the setup menu key, go into the measurement screen, and choose VPath build enable. I'm going to enable that to on, and then press the red measure. So now when I press that CalVel key, it's going to prompt me, VPath builder, yes or no? I'm going to choose yes. So again, I get this nice help text. Measure test block 0.1, then press enter to continue. So I couple onto my thick, press enter. So it says enter value for test block 0.1, so I make that adjustment. Then CalVel to measure next selected test block point. So I'm going to press CalVel. So I'm going to also do the 750. I'm going to do the 150. So I have to do a minimum of 3. If I do more points, it's going to give me a better VPath correction. But let's see, even just with those 3 points, how it does. So here I'm measuring 150. Here I'm measuring 300. Here I'm measuring 750 and 1.5. So a lot more accurate thickness measurements, because now I have a more appropriate VPath correction for this transducer. So at this point, I can save this. So if I press the save key, I can give this a custom name, and I can call it whatever I like to basically give it a unique name that corresponds to that transducer. A lot of times we also call out the material that it's calibrated for. Okay, so now I want to talk about detection methods. So there's a number of detection methods or modes that flaw detectors use, and some of the common methods really don't work that well for measuring thickness. So I really want to kind of discuss those and discuss why they're not really appropriate for measuring thickness. So the first one is going to be using flanking or edge gate detection. So this is when you set a gate, and when the signal amplitude crosses the gate, you base your time of flight measurement on the front edge of where that signal crosses the gate. So the issue with this method is it's heavily reliant on the amplitude of the signal. So if your amplitude is 60 dB or 54 dB, where that signal crosses the gate is going to vary. So your time of flight measurement is going to vary. So here you can see just a 6 dB change in amplitude actually caused an 11 thousandths or 0.28 millimeter change in thickness. So this is even more important if you're measuring an application where there's wide amplitude fluctuations, like high temp. The thickness would be inconsistent due to the amplitude changes. So the next method is using peak gate detection. So the time of flight measurement is based on the highest peak of the signal that crosses the gate. So the big thing here is measuring to the peak of the signal means that you're going to be less sensitive to internal pits. So that's what this kind of diagram here shows. There's a cleaner back surface, but then there's a pit right here. So the majority of sound is going to reflect off of that back surface and correspond to this peak here. Where in reality, the signal from that pit appears first because it has the shortest sound path. So you'd actually want to be measuring this signal. So how do we do it with corrosion thickness gauges? So we use advanced algorithms and also digital signal processing. So a lot of times the signal that you see on screen with a thickness gauge will actually be already kind of automatically controlled as far as gain goes, so that you can see the peak of the signal on screen regardless of the amplitude that regardless of the thickness that you're measuring. It's going to always have the same amplitude. So it's very clear to see that you're making a correct detection. Whereas a flaw detector, you get much more of kind of a raw output because you do want that amplitude change based on what you're detecting. So one key point here is that the echo detected is once that signal is at or above the 20% screen height. So it might be a little bit hard to see here, but there's some kind of graticule lines representing 20% screen height. But the time of flight measurement's not done at that 20% detection threshold. Once the echo's over 20%, it will start to be detected, but the advanced algorithm within the instrument will actually measure the time of flight to a consistent and repeatable point. And what this does is it allows for the calibrated accuracy to be maintained when gain or amplitude changes. So you can run the system at lower gain and yield a cleaner waveform. So here you can see a 32 dB difference in gain, and the thickness reading in both screenshots is unchanged. So I just want to kind of show that as well. So again, I'm going to share my screen. Just got to grab the transducer. So again, as soon as I plug in the thickness gauge dual, with this one it has a center pin, so it recognizes what's being plugged in, prompts me to do that auto zero, so I follow the instructions. So now if I couple on that 300 thousandths and I press the gain key, I can go all the way down to 40 dB and the signal is unchanged. So that's the lowest gain setting I can go for this transducer. Still reading 299. I can increase that gain all the way to 75 dB, right? And I'm getting the same reading. So that's a 35 dB dynamic gain range, which is pretty impressive. So you can kind of see that you get the same consistent, accurate time of flight measurement. The thickness reading is unchanged regardless if the amplitude is 75 dB or 40 dB. Okay, so next we'll talk about some of the application advantages for the corrosion thickness gauges. So this includes temperature compensation, EMAT, internal oxide, encoded B-scan, echo to echo, and through coat. So this is an example of a high temperature application. So this kind of shows the normal process of what the signal looks like. So typically you apply the couplant, which is like a paste because it's a high temp couplant, to the transducer tip. Then when you couple on, there's no signal. But as the couplant actually starts to melt, you'll get a good signal. And then once the couplant completely melts away, you get no signal. So luckily, because of our advanced echo detection algorithms, we have a consistent thickness measurement over that large amplitude change where you have no signal, get a signal, and then it disappears. The thickness reading you capture regardless of the amplitude, is going to be the same as long as that signal is over 20%. But there are some tips we recommend when measuring high temperature. You want to increase the gain about 5 or 6 dB to help get a strong enough signal when you couple on. You want to max out the update rate so that you can make the measurement as fast as possible. You also want to use that auto zero feature that we talked about. You want to use that often because it's going to compensate for the change in sound velocity in the delays. You can use the freeze key on the 38, which holds the reading on screen. So you can limit how long you have that transducer on the hot pipe. You can couple on. As soon as you get that signal over 20%, you can hit the freeze key, uncouple, and then from there, from the frozen waveform, you can actually make internal adjustments to either the gain or blanking settings. And then also, you want to use temperature compensation. So that's a unique feature on the 38 that we'll discuss. So as I mentioned earlier, sound velocity changes with temperature. So as temperature increases, the sound velocity decreases. As temperature decreases, sound velocity increases. The sound velocity in steel changes approximately 1% per 100 degrees Fahrenheit for change in temperature. So if you calibrate on a test block at room temperature and then you measure a hot steel pipe, the reading is going to be thicker than the pipe wall thickness actually is. So what the temperature compensation feature allows the user to do is enter in the temperature at calibration, which is usually an ambient temperature, the temperature measurement, the temperature at the measurement, which is the hot pipe, the elevated temperature application that you're measuring, and the K coefficient for the material being measured. So by default, the K value is for carbon steel, because typically that's what users are measuring. But you do have the ability to adjust that K value if you are measuring something other than carbon steel. So again, this allows for a more accurate thickness reading since you're adjusting you're using the adjusted sound velocity. And also it's much easier than trying to calibrate on a hot test block to compensate for that velocity change. And I'm not sure, I don't know if I said that correct, but temperature increases, sound velocity decreases, temperature decreases, sound velocity increases. Just want to make sure I get that right. So this is a screenshot of the temperature compensation feature on the 38. So you can see the current temperature of the application, and this can be easily adjusted by pressing the second F key and the transducer recall key to change that value from this main measurement screen. And then we have that compensated, or we have that thickness reading that's using the adjusted sound velocity. So the next application I want to discuss is boiler tube applications. So the very high temperatures found inside steam boilers actually cause this formation of a brittle iron oxide that's called magnetite. And this forms on the inside and the outside of the boiler tube. So on the inside of the tube, on the steam side, the oxygen in the water vapor will react with iron to form internal oxide. While on the fire side, on the outside of the tube, the oxygen in the flue gas reacts with the iron and forms external scale. So you get scale on the inside and on the outside. So the first solution is using an EMAT transducer. So you can see that on the left here. So this requires that external scale, and it's really designed to be kind of an initial screening tool to determine if the boiler tube wall thickness is still within spec. Because if it's not, then there's really no sense in doing further inspection. It's better to just kind of scrap the boiler. But if you do use the EMAT and you determine that the measurements are within spec, then what they'll do is they'll remove that external scale and do a more in-depth inspection using a single element delay line transducer and the internal oxide software. So EMAT, or electromagnetic acoustic transducer, is a transducer that generates shear wave sound energy in ferrous metals that are externally coated with high temperature oxide scale. So as I mentioned, it's really just designed to be kind of a quick way of determining the approximate wall thickness without going through the process of removing the external scale. And the E110-SB EMAT transducer we sell is a very low energy EMAT. So it's not going to work on bare metal. It does require that external magnetite scale to be bonded to the boiler tube. And to be honest, it only really kind of applies to this boiler tube application. It doesn't require couplant. It's a non-focused signal. So it's going to be kind of relatively insensitive to small internal pits. The accuracy is about plus or minus 10,000ths of an inch, or about 1/4 millimeter. And the minimum thickness is about 80,000ths of an inch, or 2 millimeters. So it's really just kind of an initial screening tool. So if they determine that the boiler is within spec, they'll remove that external scale and do an internal oxide measurement. So the internal oxide scale can actually help protect the steel from corrosion. If the tube maintains a constant temperature, the rate at which that internal oxide scale grows will normally decrease. But if the scale gets too thick, then the insulating properties of that scale is going to cause the temperature of the tube to increase, which then causes that oxide scale to grow quite rapidly. So they definitely want to monitor that scale thickness to make sure that it's not getting too thick. So what that oxide software option allows the user to do is simultaneously measure the oxide scale thickness on the inside of the boiler tube, as well as the wall thickness of the boiler tube, all with just one transducer coupling onto the part. So it's really kind of an automated system. Again, the instrument kind of does the work for the user. With this one, you do have to remove the external oxide scale in order to make the measurements. But once you have the oxide option software, it's going to unlock 2 setups for the ley line transducers that we found work best for this application. So the first is the M2017, which can measure a minimum oxide scale of about 10,000ths of an inch, or 1/4 millimeter, and also a setup for the M2091, which has a minimum of about 6,000ths, or 0.15 millimeters. And I should note that that M2091 is a shear wave transducer, so you do have to use shear wave couplant. So another application is encoded B-scan. So the 38DL Plus and also the 45MG both come standard with non-encoded B-scan. So non-encoded B-scan just runs at a fixed rate and it doesn't capture the distance traveled. The encoded B-scan option for the 38 allows the 38 to be connected to a linear encoder and actually do encoded B-scans that capture thickness and also distance traveled. What's nice is these B-scans can be saved to the internal data logger, uploaded to gauge view thickness, which you see here. Here's the whole scan. You can highlight a certain portion, do a more in-depth look, adjust the cursor to see what the thickness is at that point. So obviously, flaw detectors have an advantage with scanning. They can provide a lot more data than thickness gauges can. But the advantage with the encoded B-scan on the 38 is it's significantly less expensive, and it still allows the user to have a scanning option with a thickness gauge that tracks the distance traveled. So they can do a scan of a pipe, see where the worst corrosion is, and then go back and do a more in-depth measurement in those locations. So the next application is measuring thickness on painted metals. We actually have 2 solutions. We have either echo to echo or through coat. So echo to echo has been used for many, many years to ignore coatings and just measure the true metal thickness. And the way we do that is to measure the time of flight between successive backwall echoes. So when you do echo to echo, you have the option to choose either automatic or manual. So automatic echo to echo will automatically make thickness measurements between the highest amplitude backwall signal and the second highest amplitude backwall signal, as you can see on the left. Whereas on the right, we're doing a manual echo-to-echo. So in this mode, the user has the ability to make internal adjustments. So they have the ability to adjust blanking to eliminate any signals or shear wave components that are present between the two backwall signals. So both are a pretty automated measurement. The manual echo-to-echo just gives you that extra adjustment if automatic doesn't work. So there's no gates to set, so it's much easier and faster setup for that user. But there are some limitations, and these include measuring thick samples, since it's harder to get multiple backwall signals from a thick sample. Also measuring thin materials, and if you're measuring something that's painted that has a severely corroded backwall, because again, you're going to struggle to get multiple backwalls. So the first limitation is measuring thin materials. So echo-to-echo really won't work well if you measure thicknesses below about 80 thousandths to about 100 thousandths. On the left, you can see we're right at about that 80 thousandths or 2 millimeter measurement, and we're making a valid echo-to-echo measurement from first backwall to second backwall. But in this situation where we couple onto that 40 thousandths or 1 millimeter sample, there's just not enough separation between signals, so you're getting a false reading. So this is the other kind of limitation, is if the back surface is heavily corroded. So lots of the sound's getting scattered, and you're unable to obtain those multiple backwalls needed to make an echo-to-echo measurement. So the other option is through coat for measuring thickness on painted metal. And with through coat, you can actually measure the thickness of the paint and the thickness of the steel at the same time using a single backwall echo, as you can see here. Here's the thickness of the coating, here's the thickness of the steel. So there are advantages for through coat as compared to echo-to-echo. So through coat, due to the construction of the transducers, can measure much thinner, down to about 40 thousandths or 1 millimeter. You can also measure thick because they only require one backwall. And likewise, because they only need one backwall, they work better on a painted surface with a heavily corroded back wall or back surface. And again, it's a very automated setup and measurement. So you plug in the through coat transducer, the instrument recognizes that probe. When you do the auto zero, it's going to ask you if you want to enable through coat, yes or no. If you choose yes, automatically you get these two boxes, one for the coating and one for the actual steel thickness. So there's three through coat transducers that we offer: the D7906-SM, D7906-RM, and the D7908. So what's great about these transducers is they can be used in standard mode, through coat mode, and echo-to-echo mode. But they do have some limitations as well. So they're not going to work well on rough or textured surfaces. The paint coating has to be at least 5/1000ths of an inch, or about 1/8 of a millimeter. And they can't be used for high temperature because of the materials that the through coat probes are made out of. So I want to kind of show a demo of that as well. So again, I'm going to do my auto 0, second F, cal 0. So the three steps I'll be measuring are 300 thousandths, 150 thousandths, and 50 thousandths. I'm using a plastic card with coupling on both sides to simulate the paint thickness. So if I press the second F key and the zoom key and choose Auto E to E, you'll see when I couple on, here I'm making a valid echo-to-echo measurement between multiple signals. I'm not calibrated, but the reading is close. If I go on the 150, same thing, I'm making a valid echo-to-echo measurement. If I go on the 50, there's just not enough separation. I'm unable to ignore the coating and measure the steel. So the other example is I have a sample that has clean outer edges, but the center of the sample is corroded on the back surface. So if you see here, when I couple on to the outer edge, I'm making a valid echo-to-echo measurement. But if I couple onto that middle, there's only one back wall on screen. I'm not ignoring the coating. So a through coat would kind of solve this issue. So let's see what happens when I use a through coat transducer. So again, I'm going to do my auto 0. You'll see it asks me enable through coat, yes or no. I'm going to choose yes. Right off the bat, I get my two separate boxes for the measurements. I'm going to do the same application. Here's 300. Separates out the coating and the steel using a single back wall. Here's my 150. And then there's my 50,000. So again, I'm not calibrated, but you can see using the through coat, I can measure a lot thinner. Also, if I go on my heavily corroded sample, I'm able to separate out the coating and the steel using a single back wall. Okay. So next I want to focus on a couple gauge features. So this kind of goes back to the users of the instruments. Because our users are a little bit less trained, we build in these features to help prevent incorrect calibration and ultimately incorrect measurements. So they include doubling warnings and gain optimization. So what is doubling? So doubling is when the gauge detects the second back wall reflection and misses the first back wall. So what causes doubling? So when you use a dual element transducer, the echo from the first back wall is not always the highest amplitude signal. And this is caused by the roof angle and focus of the transducer. So if you try to use a dual on something thinner than it's rated for, you might experience doubling. Also, if the transducer is worn, it'll cause the signals to be lower in amplitude, so doubling can occur as well. And this is a common error that we see from users. So the blue lines represent the first reflection off the back wall, and the red dashed lines represent the second multiple off of the back wall. So you can see on the left on the thick sample, on the left, on the thick sample, the first back wall echo is above the 20% detection threshold and it's being measured. Everything's good. You'll notice the second is lower in amplitude. However, on the thin sample, the first back wall echo is below that 20% detection threshold, and the gauge actually reads to the second back wall. And what it does is gives a measurement that's twice the actual thickness of 0.1 inches, because what the gauge is doing is it's measuring twice the time of flight. So you end up getting a reading of 200 thousandths or 5 millimeters instead of the 100,000ths or 2.5 millimeters that's the actual thickness. So at thicknesses greater than the focus point of the dual element transducer, the first back wall is going to be the highest amplitude echo. But if the thickness is below the focus point, then that first back wall is not going to necessarily be the highest amplitude echo. So this is why doubling typically occurs on thin samples and not so much on thick samples. So we actually build in a warning because of this. So we have what we call the calibration doubling warning. So when you do your cal-vel on your thick, the instrument already kind of knows what the time of flight value should be based on what it determined in the cal velocity. So what it does is it compares the time of flight from the thin test block, cal 0, to the expected time based on that cal-vel. And if it all of a sudden sees that this time of flight measurement is too large and is out of tolerance, then it's going to pop up with this message, potential wrong echo detected, kind of notifying the user that this isn't the correct detection point and you're making a false reading. So how would you correct this? So you'd increase gain. So you basically increase the gain enough so that that first signal is above the 20% detection threshold. So you'll see now on the left in waveform 1, everything's still good, but on the right, waveform 2, that first signal is above 20% and is now being detected. It's still not the highest amplitude signal because of the focus point, but it is above that 20%, so it starts being detected. So I actually want to show an example of that as well. So I want to make sure that my VPath builder is off, which it is. So I'm going to do second F and then do 0. So I'm going to bring the gain down on this transducer just to simulate what a worn transducer would look like. So I'm going to drop this down to about 13 dB. So you can see here, still reading 750, it's reading 300, but then it's reading double thickness. So see what happens when I calibrate. So if I press cal-vel, couple on to my thick, adjust that to 750, press cal 0, couple onto my thin, press enter, and then press measure. So potential wrong echo detected, continue yes or no. So I'm going to choose no. I'm going to go back to that thin sample. I recognize now that it's a potential wrong echo because the instrument notified me of that. So I'm going to press the gain key and bring it up so that that first signal is above the detection threshold. So now I can go through my calibration, measuring to the correct signal. So then we have gain optimization calibration. So this comes standard on the 38. It's called gain opt for short. So it's turned on in the setup menu, and it's done during the calibration procedure. And what it does is it sets the ideal gain setting based on that specific transducer and the thickness range and material that's being measured. So it's going to automatically set the appropriate gain. So you'll see when I do the live demo that it eliminates the doubling issue right off the bat because it adjusts that gain as needed. So again, this is a tool for a less trained user where they can have the instrument set the gain for them. Because setting the appropriate gain is going to give the user the best chance of making accurate thickness measurements. So this also helps increase the useful life of the transducer, but most important, it prevents calibration and measurement errors for the user. So I want to show that as well. So again, I'm going to bring my gain down to about 13 dB just to simulate that worn transducer. So I'm doubling on that 150, measuring OK on the 300 and OK on the 750. So if I press the setup menu key, press the right arrow, and then down to gain opt. So you can see gain opt and VPath bill both come standard on the 38. I'm going to switch that to on, and then press the red measure key. So now I can go through my calibration. So I start off by pressing calvel, follow the help text to measure thick standard, and then press enter. So there is a little bit of a lag just because the instrument's doing some additional processing based on that calvel point. It's looking at the amplitude of that signal and relating that to the noise. And you'll see when I do the cal 0 and couple on, my gain has already been increased, so I'm not getting that doubling issue. I'm actually measuring the correct back wall because the instrument optimized my gain setting. So from here I can press enter, adjust this to 150, and then press the red measure. So down in the bottom right you can see it increased my gain to 36 dB, which is an ideal gain setting for this transducer. And all my measurements are linear. I'm not doubling any longer. So gain opt really takes the gain adjustments out of the user's hands and just automatically sets the appropriate gain for that transducer. So both that and the doubling warning is really just to help prevent incorrect calibration. So that's the webinar. I want to thank you all for your time. Both Olympus product lines are excellent. Both thickness gauges and flaw detectors are great instruments. And again, it really comes down to the application and what are you measuring. So if you're detecting flaws or voids, checking welds, and you also want to measure thickness, you're going to want a flaw detector. But nothing's going to really beat an Olympus thickness gauge if you want the most accurate, repeatable corrosion thickness measurements. And what's nice is they're small, powerful, less expensive instruments. So thank you again for all of your time. If there's any questions in the Q&A section, it looks like we're almost out of time. So we'll be sure to follow up with those as well. I'm just going to hand it back over to Greg.
Thanks, Greg. On behalf of Olympus, I'd like to thank all the attendees for joining us today, and Greg for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar, along with Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for attending, and we'll see you again next time.